if you have a function that you rotate about the x-axis, you would generate a volume. You can spin it about the y-axis, you generate a volume. But every 3D object that you have has volume, but it also has area. Do we agree? Now, that is not the same area as, say, the area of a circle. Why? You look at my coffee cup, this bottle that someone left. Yeah, true, but this might be a good example. Looks like a cylinder chopped up. It has volume, right? But it also has an area. But it is not the same area as the area of this table. We have a very specific name for it. Starts with the letter S. Surface area. So the outer part surface of this cylinder, or bottom, which is in fact the shape of the cylinder, if you chop it off here, that has volume and it has surface area. So if you have a function, spin it about the x-axis, you are going to get a surface, correct? Yes, no, maybe. And depending on the type of function you have, say if you have area enclosed by two curves, you can still find the area, correct? Because even if you have a hollow object, it has a surface. That's it. What if you don't have a function? Rather, you end up having weird looking curves of some sort, and you spin it about an axis, and you want to find its area. Painful? Not painful if you have a parametric equation. Last time, when we used to find the length, when we used parametric equations to find the length of a curve, how did integrals come into play? It started with the guy Pythagoras, then we went to Euclidean distance, the different formula. From there, we went to delta notation, made uppercase delta to lowercase delta, did a bunch of algebra, used the Riemann sum, we got the length. That was the approach. Once we had the length, we just rewrote it in terms of dy over dt and dx over dt. So if we want to find the area, we need the surface area to be precise. We need to follow a similar strategy that we did with length. Spinning about the x-axis is easier to follow, so I'm going to go with that. Let's say that that is my shape. Good. And you know, if you covered it, that'll be like the shape of a peanut, right? Boiled peanut, whatever. Let's say if someone wants to know the surface area of boiled peanut, it's not easy, correct? But if you can come up with a parametric set of equations to represent the edge or the outline, then you can get the surface area of boiled peanuts. Yes. Of course, not every peanut would have the same curve, correct? They differ, but we can make an approximation. So, what is the idea? Well, we spin. What were the steps in volume? What did we do in order to get the volume? The process. I said, first you've got to do this, and if you do this, then you know how to set up your integral.
You determine
Very good, dy dx, Alex.
Just say sketch it.
Let's sketch it, and in that sketch, your answer is related to Alex's answer. In that sketch, you've got to put something very important. No,
You have to draw the strip.
the strip. The strip is the most important part. The strip is going to tell you how to set up the integral. How do we get that knowledge? By sketching. You sketch, you know where to put that strip. So strip again. Well, no, didn't sound right. Draw this strip. Dx. And this strip is going to move along that curve. Agreed. Okay. What were the methods that we saw when we did volume? We covered 3 methods.
Cylindrical shells.
Cylindrical shells. Washer, yes, by all means, washer method. The special case would be this. Okay, so we could do cylindrical shells on this as well. Yes, no, maybe. So if I put a cylinder just half of it, I have a radius and I have height. Agreed. So as I move this strip along, what value does it change?
The what?
The y value. Y gets changed as I move this way. What is the surface area of a cylinder? Do we not know the surface area of the cylinder?
2 pi r h.
Very good, 2 pi RH. If you understand what's going on, you don't have to memorize it. Right, just a thin string outside. If you take a string, or I'm used to hairbands, because obviously, so if you have a hairband around a paper towel or cheap toilet paper roll tube and move that band along, you will sweep the area of that tube. Do you agree? Yes. So imagine that that is the hairband and you are sweeping it along the third dimension or up that way. That will be the height. Yes. The band, if the radius is in the middle, what is the length of the band? The hairband that goes around the tube.
2 r.
2r, that's the diameter.
2 pi r.
2 pi r, so that is the circumference, and that would be 2 pi r. Yes. So if you infinitesimally add 2 pi r's h times, what do you get? 2 pi rh. Yes, you don't have to memorize this. You understand the concept. Likewise, you don't have to memorize the area of a cylinder. Same logic. that is the area now. Yes, so you have a circular sheet and think of a slice of cheese and you stack a whole bunch of slices. What do you get? A giant block of cheese, a cylindrical block of cheese. And if each slice has an area of pi r squared, you're stacking h of them. What is the volume? Pi r squared h. Yes?
So by
Yeah, volume. No need to memorize. You could do the same for a cone, for a sphere, and so on. There is a trick that would be useful in calculus 3. Who's going from calculus 3? Okay, so whatever you learned here is extended to calculus 3, and whatever we learn here would apply to n dimensions. And calculus 3 is just the third dimension. So you started with 1, then 2, now 3. 1 dimension is length. 2 dimension area. 3 dimensions volume. Yes. The nice thing is if you keep on moving this way, you can go backwards also. Yes. I start a whole bunch of cheese slices, circularly shaped, h times to get pi r squared h. If that is the case, I can go in reverse. Yes? Integrated. What is the backwards operation of integration? Derivative. You just go backwards. Derivative. So, key concept. If you took the derivative of dv with respect to r, volume becomes area. What is the derivative of pi r squared h with respect to r? 2 pi r h. Good. That is a trick that you've got to know for calculus 3. Okay. Good. Okay.
that's crazy.
Yeah, it's great indeed. And the nice thing is, whatever that works for the first, second, third dimension, will work for n dimensions. Erase. So the point being,
The derivative of s. Would that be like,
exactly.
what is it? Pi r h?
You have to take the derivative with respect to height. You've got to know which dimension you're eliminating, right? To get that surface area, that hairband moved along the tube, right? Which is the height. So if you have to go back, you would take the derivative with respect to h. Well, that will give you 2 pi r. But what is the length of the hairband? 2 pi r. Good. You just have to know which variable you're taking the derivative with respect to. But I digress. So the point there is you need the radius, you need the height, and we are integrating. So integral, we have a starting point, we have an ending point, so A to B. And I am moving along Y. In other words, I've got to cover that entire length because that length is what's going to spin about, correct? Just like the hairband moving across that tube. With me? So when you spin, this curve is what's going to move this way, creating an area. So 1 full circle, so 2 pi. That's 1 point right there. I put it as x, but infinitesimally small interval x. So we will have dx. Yes,
What point is x?
the strip.
Okay.
Length of the strip. So now if I move the strip back and forth, it is going to move along that length, but no matter, or depending on where I put that strip, I'll have an X value, I'm going to have a Y value, agreed? The Y value is going to determine the height, yes? Cylinder length, this way, height, so Y would be the height. The radius would simply be the length of that curve as you move along the x-axis. Do you agree? At each point, that will be the radius and keeps on going. So that bit right there would be that infinitesimally small length of curve. Call it L. I'm going to replace it quickly. So A to B, 2 pi, we'll call it f of x. Y is f of x. Doing it in functional form first. Length. We had a formula for length. It all started with Pythagoras, then Euclidean rate of change, and I rewrote it as the square root of something. Do we remember? In case you forget, it all comes from the distance formula, yes? The change, we wrote it as delta y, delta x called delta xl. So square root of 1 plus dy over dx squared. The dx that we pulled out is what's going to be there also. So all of that would form the length at each point, infinitesimally small interval. And you are multiplying that by f of x, which is the height. So pretty much you are doing 2 pi r h. Good. Rewriting the radius and rewriting the height. So if you know a function, then you can put the value of the function on the interval, find its derivative with respect to x, do that stuff, and you will get the surface area of whatever solid that you would have when you spin it about an axis. Yes, are we clear? Okay, what if we have a funky curve? Let's say kind of takes around and goes like that. If you spin it, would you get a volume? Why not?
It wouldn't be like a closed, it would. I don't know how to describe it.
Yeah, right. So would it have a volume? Sure, it is going to have a volume up to that part. It is not going to have a volume there. It's going to be, well, perhaps it will, right? It will have, you spin it this way, it will have volume there. In a weird shape, there'll be a volume, and then you'd have volume there. It will have a volume of some sort. So it must have an area also, agreed? But unfortunately, we can't use that. Why? It's not a function. So if I can come up with a set of parametric equations, then I could use that parametric equation, use the logic that we have with the function, extend it, and we'll have the answer. Does that make sense? Yes. So how did we rewrite the length in terms of parametric equations?
The square root of dx over dt squared
That
plus.
erase this stuff.
Yeah.
Didn't mean to interrupt, Caitlin, go ahead.
The integral of the square root of dx over dt squared plus dy over dt squared.
And we integrated with respect to what letter?
T.
T. And mind you, T is the path that you form, and whatever limits that you have must be for T. So I'll call this T1 to T2. Also, whatever we do with functions, if you can go back and forth, the xy value here would correspond to a t value there. You can make that direct connection when you parameterize. Okay, so that would cover the length part. Yes, dx becomes dt. T1 is simply the t value corresponding to A. T2 is the t value corresponding to B along the path of some curve. Leaves us with just two parts, 2 pi and y. We know in parametric equations, x is a function of t, y is a function of t. So we know, I don't know if I've rated specifically, x is some function of t, y is some function of t. So the surface area in this case would be T1 to T2, g of t square root of dx over squared, dy over dt squared, dt. Calculus 1, calculus 2, calculus 3. Length, area, volume. Yes, basic integral. Moved on to area. What are the things that we did? Now we are at volume. You will be at volume 3 dimensions. But it all started with the basic principle of extending derivatives and integrals to the next dimension, correct? So I moved from here, used the exact same concept to this. Well, where did that come from, which we used in calculus 1 and 2, goes back to algebra. Algebra, distance formula, but where did distance formula come from? Geometry. And who did that geometry? That's one guy. That's algebra. Okay, connected the dots. Does that make sense? Why am I going through this? If you understand that concept, you don't need a cheat sheet. It'll just come naturally. Are we clear?